All right, hey everybody, we're going to continue our discussion of the Heck reaction by focusing on the reaction mechanism. Before we do that, we need to talk about what the active catalyst is. As I said, the palladium diacetate catalyst is really palladium 2, but it's thought that the active catalyst in the palladium reaction is, in the Heck reaction, is palladium 0. And there's a couple of different ways that you could think of this happening, and there's I'll show you something. It's not in the text, and it's sort of beyond the scope of what's going on here, but it's thought that this is how the palladium 2 that you start with gets reduced to palladium 0 so that the catalytic reaction can start. As to why they don't just start with palladium 0, I'm not sure. And that's something that I'm sure that they've looked at. Presumably the reaction works better when they use palladium 2 as the starting material. In any case, it's thought first that there's ligand exchange between I'm trying to decide whether or not we dare do this or whether we should just proceed onward. Um, so here is palladium acetate. You've seen this organometallic complex before. Two L-type ligands, two X-type ligands. Overall complex is neutral, so it's palladium 2. There are 8 d electrons, and overall there are 16 electrons overall. So it's not coordinatively saturated. The reaction can undergo ligand exchange if we start to add the orthotolulyl phosphine, which I'm going to abbreviate as PR3. We can get palladium bound to multiple phosphine ligands. It's thought that one such intermediate might look like this. Of course, you can imagine palladium, if you replace X-type ligands with L-type ligands, now the complex overall has a charge. You could put any number of neutral ligands on the palladium, it's still palladium 2. It's thought, one potential mechanism for conversion of palladium to here to palladium 0 is binding of acetate, which I'm going to abbreviate like this, to the metal to create the following complex. And again, what I'm showing you is cobbled together from a couple of different sources. It's outside the area of my expertise, and it's beyond the scope of what I might ask you on an exam, but I do want you to have some idea of how you get from palladium 2 to palladium 0. It's somewhat unsatisfying in the text to say, yeah, we're using palladium 2 as our reagent, but the active catalyst is palladium 0. It's thought that what may happen is essentially a reductive elimination step in which an oxygen from the acetate ion attacks phosphorus and these electrons go back on palladium. Overall, this complex after acetate binds should be sort of +1. Afterwards, it's just palladium bound to the 2 phosphine ligands. we've lost a phosphine ligand and we've lost an acetate. Before we had 3 L-type ligands and 1 X-type ligand, and the overall charge was +1, which means we were palladium 2. Afterwards, we've lost it'll be easier to see what's happening here if we follow along. We've lost this weird phosphorus species. There goes our positive charge. The remaining complex is neutral, which means we've gone back with 2 L-type ligands. We've gone back to palladium 0, 10 d electrons. How did we get from D8 to D10? Well, the 2 electrons that were in this phosphorus palladium bond go back onto the palladium. Effectively, palladium gets reduced, and that is now your active catalyst in the Heck reaction. All right, with that in mind, let's sort of draw the catalytic cycle for the Heck reaction. I'm going to need a new page to do this. We start with the palladium 0 bound to the 2 phosphine ligands. And we're going to do an oxidative addition step. And we're going to do that with, let's do this reaction. So I'm going to copy those starting materials. Sorry for the trouble. Sorry to skip up and down. So we'll do oxidative addition of this vinyl halide. Again, oxidative addition is going to involve basically 2 of the d electrons on palladium. That's palladium 0, D10, 10 d electrons, and then in terms of overall electron count, 14 overall, so it's not coordinatively saturated. There's a place for some new ligands to come in. After we do the oxidative addition, that's going to involve 2 electrons from palladium forming a palladium carbon bond, and then the 2 electrons from the carbon iodide bond forming an iodide palladium bond. There's an alternative way to think about it that we've talked about earlier. I won't say anything more about that. The stereochemistry of the vinyl halide is preserved. The iodide is trans to the ethyl group before oxidative addition. Similarly, the palladium will be trans to the ethyl group after the oxidative addition. And then you have the 2 remaining phosphine ligands. Only I'm not using the pH because they're not phenols. They're just ortho-tolulyl groups, but we'll abbreviate them as R. We now have 2 X-type ligands and 2 L-type ligands. So this complex overall is a palladium is now a palladium 0 complex, or rather, sorry, oxidative addition. The overall complex is neutral. Now this is palladium 2. It now has 8 d electrons, but 16 total electron count. And that's important because the next thing that appears to happen in the Heck reaction is a ligand binding step. And so what will happen is that the pi electrons from the olefin sorry, I'm not liking how I drew the arrows there. My apologies. are going to coordinate to the palladium metal. We can show this process happening by drawing palladium with a dotted line here. Here is the olefin, and it's the pi electrons from the olefin that are coordinating the palladium as an L-type ligand. If it's okay, I'm going to represent this molecule with a Z just to make the drawing easier. And then we still have these other groups on the palladium. We have the iodide, we have the two phosphine ligands, only they're not triphenylphosphine. How many times am I going to make that mistake? They're an R3 group. Overall, the complex is still neutral. You have two X-type ligands and three L-type ligands. That means you're dealing with palladium 2. It's still D8, but now the total electron count is 18, and now we are coordinatively saturated. So what happens next is interesting and kind of weird. The next step is called migratory insertion. And I will push arrows here because it's important for sort of figuring out what's going on. We're going to take the electrons in this carbon palladium bond involving the vinyl group, and we're going to move them from migrate them from being on the palladium to being attached to the less substituted carbon of the olefin. For our purposes here, it might be useful to call this carbon 1 and carbon 2. And I'm sorry, I think I just switched our colors. So let's have this be our orange carbon, and then let's have the olefin portion be blue 1 and blue 2. So we're going to take the electrons in the carbon-palladium bond and we're going to have them attack carbon 1. At the same time, the pi electrons from the pi bond between 1 and 2, the ones that are coordinating palladium anyway, are going to form a full bond with palladium. And maybe I need to redraw the olefin just here are the pi electrons. So we're going to form a new bond between blue 1 and the orange vinyl carbon. And at the same time, those pi electrons that were coordinating palladium in the first place are going to make a new bond between blue 2 and palladium. So after the migratory insertion, this is what we're going to have. You've got palladium. Here is the new bond with blue 1. Or sorry, here's the new bond with blue 2. And then here is blue 1. And then here is the new bond with the orange vinyl carbon. Again, the stereochemistry about that orange vinyl carbon is going to stay the same, so it's still going to be E here. And then on the remaining portion of the metal, we've got this. So notice we're still, overall, we've still got two X-type ligands and two L-type ligands. Overall complex is neutral. This is still palladium 2. Still got 8 d electrons. and now it's now only got 16 electrons total, because we took 2 electrons away from palladium in this carbon-palladium bond and we made a new carbon-carbon bond. Okay. So in this migratory insertion step, we tentatively lost the pi bond on our olefin partner. See that pi bond that was in our olefin partner? It is now gone. Here's carbons, sorry, I'm jumping around real quickly. Here's carbons 1 and 2 on the olefin, 1 and 2. That pi bond is now gone. And what follows is a new step that is unusual. And it's one that, in order to understand, you gotta consider the hydrogens that are on carbons 2 and 1. I'm going to show you this. It's beyond the scope of the class. Your text doesn't talk about it at all, but it's important for helping you understand what happens. Okay, so here is our intermediate. And I'm going to redraw this intermediate in a way that reflects what has to happen at the next step. So I'm going to try to erase some of the extraneous things. For the next step to happen, we have to rotate around the bond between 1 and 2 such that one of these 2 CH bonds is coplanar with the carbon. One of these CH bonds on carbon 1 has to be coplanar, syn coplanar, with the bond between palladium and carbon. So if we rotate, and just for the sake of argument, it may be useful for us to just pick, let's let that CZ bond be a wedge and this CH bond be a dash. Okay. I'm going to continue to do that here. This CZ bond is a wedge, this CH bond is a dash. But we need to rotate around the bond between carbon 1 and carbon 2 such that one of those 2 CH bonds on carbon 1 is syn coplanar with the carbon palladium bond. All right, so let's have it be this one. I'm going to drop the labeling of bonds in red in our redrawn molecule. Okay, so here is one option. In one of these options, the orange vinyl carbon, I'm going to label what was the halide carbon on our vinyl group and what was the terminal carbon on our olefin. I'm going to continue that labeling here. In this conformation, one of the 2 hydrogens is now syn coplanar with the carbon, this with the CH bond is syn coplanar with this CPD bond. But notice in this conformation, these 2 groups, the Z group and the vinyl carbon, are eclipsed. So that is introducing some substantial torsional strain. There's an alternative, of course. We could continue rotating around that carbon-carbon bond. I'm going to erase the groups just to show what it would look like after we rotate. If we rotate around that carbon-carbon bond, we get the second hydrogen here. and the orange vinyl carbon is going to be here. Okay. The Z group and the vinyl carbon are eclipsed in the conformation to the right. Left. I get left and right wrong every time. Sorry about that. The Z group and the olefin group are eclipsed in conformation 1. They are not eclipsed in conformation 2. In conformation 2, Z and H are eclipsed, and then H and vinyl carbon are eclipsed, which is a better situation overall, where we had Z and vinyl carbon eclipsed and then also H and H eclipsed. So conformation 1 is less stable. Conformation 2 is more stable. And this allows, and this is why the reaction proceeds from conformation 2. What's going to happen next is what's called a new mechanistic step, one that you haven't seen before, but one that is common in organometallic reaction mechanisms, and this is called beta hydride elimination. And I will push arrows for this. It involves essentially electrons from the carbon palladium bond leaving to reform the new pi bond. Notice that groups, as that pi bond forms, groups that are eclipsed will end up on the same side of the new pi bond. So the Z group here is going to be cis to this H on carbon 1, but trans to the orange carbon, the orange vinyl carbon. That establishes the trans selectivity that we talked about before. At the same time, electrons in this carbon hydrogen bond leave and get delivered to the palladium. After beta hydride elimination, our product is released. So I'm going to just copy this product here, and we'll put it here in our mechanism. I'll shrink it down just a little bit. That's the product that gets released. And then what does our complex look like after that beta hydride elimination step? We'll go ahead and draw it. It's now palladium bonded to hydrogen and iodide and the two phosphine ligands. Overall, our complex is still neutral. It still has two X-type ligands and two L-type ligands. So it's still palladium 2, still with 8 d electrons, and now with 16 electron count overall. And then the final step is reductive elimination. Whereby you can think of it this way, that electrons in the hydrogen, or you can think of it a couple different ways. Electrons in the hydrogen palladium bond attack the iodide, and then electrons go on to palladium, or vice versa. Iodide attacks the hydrogen and electrons go on to palladium. In any case, what gets removed is the acid HI, which immediately reacts with your triethylamine base to give you the product I minus and the corresponding triethyl ammonium ion. And that helps drive the reaction forward. So the Heck reaction is more complicated, whereas the Suzuki reaction only involved 3 steps. The Heck reaction involves oxidative addition, ligand binding, and what I've shown you here is definitely in more detail than shown in your text, then migratory insertion, followed by beta hydride elimination, followed by reductive, beta hydride elimination, followed by reductive elimination. And that's the overall mechanism for the Heck reaction. You've seen it here. You can have a chance to review it. It will be in the posted notes. I do want you to recognize oxidative addition steps. I do want you to recognize ligand binding steps. I do want you to recognize reductive elimination steps. I do want you to recognize migratory insertion versus beta hydride elimination steps. All right, so practice that for the Heck reaction and be able to predict products and provide reagents and so on. All right, the next couple of reactions that we're going to talk about involve sort of are carbon-carbon bond forming reactions, but don't necessarily don't necessarily involve transition metals. One of them will, one of them won't. These are reactions of molecules called carbenes, or in a later case, a carbenoid, in the synthesis of cyclopropanes. And it doesn't necessarily fit neatly in other chapters, so we'll just sort of show it here. As we introduce this, we need to define what a carbene is. A carbene is an unusual species in which carbon is bonded to 2 R groups, but only has 1 lone pair. Notice that this carbon is neutral. It has a 0 formal charge. The carbon is surrounded by 3 groups, but this carbon only owns 1, 2, 3, 4 electrons. All of its lone pair, all of the electrons in its lone pair, and then half of the electrons in its bonds. You can think of the carbene as though it were essentially sp2 hybridized, with the lone pair in an sp2 type orbital and then the p orbital is empty. So a carbene is, and you can even imagine that this sp2 orbital has a negative charge in it and the p orbital has a positive charge in it. That's an oversimplification, but you can think of a carbene as having dual character. It is an electrophile in its empty p orbital, and it is a nucleophile in its lone pair. And so carbenes are able to do interesting reactions that involve both nucleophile and nucleophilic attack and electrophilic attack. For example, imagine this alkane with pi electrons, and then imagine this this carbene, which, as I've said, has an empty p orbital and then a lone pair in a filled sp2 orbital. Pi electrons from the alkene can attack the empty p orbital to make a new carbon-carbon bond, And at the same time, lone pair electrons on the carbon in the filled sp2 orbital can attack the other carbon of the alkene. And this will make two new carbon-carbon bonds. Oops. Where this portion of the molecule that was on our carbene is now at this vertex of the cyclopropane, and these two carbons in the alkene are now this side of the cyclopropane three-membered ring. And this is called a cyclopropanation reaction. And it's something that works well with carbenes, and this can be a useful strategy for making various cyclopropanes. For example, your text points out that the following molecule with a cyclopropane ring in it of this kind of structure is found as a naturally occurring insecticide from chrysanthemums. I'll just draw the structure for you to illustrate it. You can already see the portion of the structure that's important that we're going to be talking about. The rest is just details. But organic chemists look at that and think, hey, I could have made that from a precursor using carbene type chemistry. And there are synthetic examples, synthetic derivatives of this naturally occurring biodegradable insecticide that you can make using this kind of cyclopropanation chemistry. So let me show you some examples of forming cyclopropanes using carbene type chemistry in organic chemistry. Carbenes are very reactive, and so it's often true that instead of using synthesizing the carbene and then storing in a bottle and using it later, you have to synthesize the carbene and use it what's called in situ. That is, you make it and then you do the reaction all in the same pot. What I'm going to show you for the first reaction in this portion of the chapter is an example of that. So let's take this olefin, this trans alkene, and then the reagents of choice are chloroform, CHCl3, and then a really strong base, which is often potassium tert butoxide, which is just potassium is the counter ion and tert butoxide is the base. And what this will do is it will make this molecule plus its enantiomer, depending on whether the carbene gets added to the olefin from above or below. So let's show you mechanistically what's likely going on here. The carbon-hydrogen bond of chloroform, because of the electron withdrawing nature of the nearby chloros through electronegativity, is somewhat acidic, at least enough that it's reasonable for butoxide to remove the proton. That gives you the following negatively charged intermediate carbanion, negative charge on the chloro, and then one of those chloros can up and leave to give you the neutral carbene. It's called a dihalocarbene because there are two halogens on the carbon. You can see the filled sp2 orbital corresponding to the lone pair and the empty p orbital, which I need a little bit more space to draw, on the carbon. Then this will react in the same way that we saw before. Let me move the term dihalocarbene here. Here is the olefin, No, sorry folks. There we go. That's better. Mechanism should proceed as follows. Pi electrons attack to form a new bond between one of the carbons of the olefin and the carbene carbon. We're attacking the empty p orbital at the same time and in the same concerted step. Lone pair electrons in the filled sp2 orbital attack the other carbon, and this gives us that product. Notice that the reaction is stereospecific. I start out with the trans olefin, and in the cyclopropane product, the methyls are still trans to each other. So naturally, you would expect if you used the cis olefin that you would similarly get a product, a cyclopropane product, in which the two methyl groups were cis to each other. And this is indeed the case. So this is, I'll just draw that product for you here so that you can see what we're talking about. Okay, there you go. So this is an example of a stereospecific reaction. Now, what if you don't want halo groups on your cyclopropane ring? Do you have some other options? And the reaction is, the answer to this is yes, you can do the reaction with just regular CH2 carbene, although that carbene is pretty unstable and involves reagents that decompose easily. And so if I want to use CH2 carbene, I need another approach, and this is what's called the Simmons-Smith cyclopropanation. This is presented in your text without a huge amount of mechanistic detail. I'll follow your text pretty closely. The Simmons-Smith cyclopropanation, like what I showed you before, is going to involve an olefin and then is going to involve diiodomethane. You can swap out what the olefin is. The diiodomethane appears to be what you're using for the Simmons-Smith cyclopropanation in all of these cases. The reagent that you use is a combination, an amalgam of zinc and copper. And the product is, again, stereospecific. The two methyl groups that are cis to each other in the starting material end up cis to each other in the product. And what gets added to both carbons of the olefin is this CH2 group. So how does this occur? I'll draw you some of what's in the text and maybe provide just a little bit more mechanistic detail. Here is the diiodomethane. And then zinc will undergo what would be called oxidative addition. Zinc is going to insert itself between the carbon iodide bond. Essentially, you could imagine lone pair electrons on zinc attacking the carbon and then the electrons in the carbon iodide bond and leaving and going to zinc. But the intermediate that forms afterwards looks like this. And you can think of this as a carbenoid, where the electrons in the carbon zinc bond are nucleophilic, like the filled sp2 on a carbene. And then here I'll use maybe green for the carbon iodide bond. Here I've got a leaving group, which is not left yet, but the sigma star between that carbon iodide bond could be a lot like the empty p orbital on a pure carbene. So this is going to be electrophilic. The carbon iodide antibonding orbital is somewhat like the empty p orbital on the carbene. So you can see this this product, which is sometimes called the Simmons-Smith reagent, as being somewhat carbene-like. So let's show you how this carbenoid, and maybe I'll move some things down and move it around to make a little bit of space for showing you the arrow pushing for this Simmons-Smith cyclopropanation. Let's take this time, shall we, let's take the same cis alkene. Pi electrons will attack the antibonding orbital of the carbon iodide bond. Sorry folks, I don't like how I've drawn this or set it up. Give me just a second to move things into the right place. I'll draw that olefin again. All right, we'll have the pi electrons attack the leaving group and iodide leaves. And then at the same time, electrons from the carbon-zinc bond will attack the other carbon, and zinc will go off on its own. That gives us our new cyclopropane ring. And then I minus ends up being bonded to zinc. In fact, you can even show that process happening as the leaving group leaves. We can take these electrons in the carbon iodide bond and have them go over to the zinc. And so the byproduct of this reaction is diiodo-zinc. And there's our cyclopropane product. All right, that will basically do it for Friday's lecture. I may have a couple of more examples of the cyclopropanation reactions to do. Then we have one more reaction in chapter 28 that we didn't talk about. It's very important. It's called olefin metathesis, and so I'll take time on Monday to do that. And then we'll see how far we get. If you're following along with the study guide in chapter 28, plan on learning to do olefin metathesis in that chapter. As to whether or not we will continue onward with chapter 29 and are there any practice problems to do there, stay tuned. I'll try to give you details as soon as I can. Thanks and have a good weekend.